In this video, I'm going to talk about how to create a power budget for your project. Now, the purpose of a power budget is to help you determine what's going to use power in your system, how much power it'll use, and then use that information to figure out how big of a power supply you need in order to supply your system so that it'll work correctly. Now, in the case of a power budget, we're looking at primarily the major components in your system. Now, what is a major component? A major component is a component that appears on your block diagram in general. So anything that's like a sensor or an actuator or a driver chip or a display or your microcontroller, anything that's likely to use more than, say, 20 milliamps of power, so a lot of power in your system in its active mode. Now, what this leaves off are things like resistors, capacitors, passive components. Wires don't usually take a lot of power, so those are not things that need to show up on your power budget. Now, I'm going to walk through an example power budget here and talk about all the different sections of it. The first step is to figure out, again, what are your major components. So this is an example for a typical system of things that you might see. So maybe you have a solenoid or a stepper motor. You have your microcontroller. You might have some sort of communications like a Bluetooth. And then also you have regulators. Now, this is the part where it's a little bit iterative because your regulators use power, meaning that they need to be documented in this spreadsheet. But later on, you can't choose the regulators until you know how much power you need. And so it's kind of a chicken and egg thing. So you might need to add the regulators after you pick out all the rest of your other major components and put them in. This next column is where you put in the actual part number for the part, and there's been some confusion as far as what is a part number, so make sure that you have all of the letters that go after the part number. If there are special packaging letters, anything that the full part number, so don't put in just, for instance, the number of the entire series of 150 chips. Supply voltage range. This is something that you're going to get from the data sheet. So as an example, I'll use this 3.3 volt load dropout regulator, and I've got the data sheet here. And when you scroll down in a data sheet, you'll find on the first page usually some sort of part number information, some sort of ordering information, and different manufacturers put them in different places, but somewhere there will be a section that is called something along the lines of absolute maximum ratings. And the key things that you want to look for here are what is the voltage range that you can supply your device with. And in this case, we have a maximum input voltage of 20 volts. And because it's a regulator, usually for regulators, there is a minimum input voltage as well that you find in another section of the data sheet. But for the purpose of this here, we care that it is 20 volts. And then, so we'll go ahead and update that to say 20 volts. And then we also care about the maximum current that the regulator can draw. So, or whatever the device happens to be can draw. And so in this case, for the regulator, it is listed as output current, and that is the maximum current that it can produce, which is 0.5 amps. And so that's going to be the value that we put over here in absolute maximum current. Now, you might ask, well, there are lots of different current values for various devices. How can I find the biggest one? Well, first of all, it's usually the current that a device uses is sometimes limited by the amount of I/O pins. So meaning, let's say that you have an FPGA that you're using, and there are a particular number of I/O pins on that FPGA, and you want to turn them all on at once. Well, that's possible, and let's say each one puts out 20 milliamp or uses 20 milliamps, and so that's great. You can theoretically turn them all on. But if you look in those absolute maximum ratings, there is typically a maximum current that is smaller because the heat dissipated by the package is really the limiting factor in the amount of current that can be drawn by the chip. And so that's the thing that you need to make sure and find in your data sheet. And in this case, it is 0.5 amps. Quantity is important because if you're using 5 of a device, then you need to obviously count that into your budget and then calculate your total current for each of your devices from there. Now, once you have your major components, you want to assign those to power rails, and this is another iterative process. So the goal is you want to have as few power rails as possible in your system, to the point that, let's say that I have a system where I have 3 power rails like this, where a 12 volt, a 5 volt, and a 3.3 volt power rail. If I only have one part on the 3.3 volt power rail, like I do here, this Bluetooth transceiver, then it behooves me to go and try and reselect that part and find one that runs at a system voltage that everything else is running on. Because the more power rails you have, the more regulators you need, the more support circuitry for those regulators, the more wires running on your board. It just makes your entire system more complex. So the goal here is to take the parts from step 1 and then assign them to different power rails based on that supply voltage range. So here, for instance, we know that we have a solenoid and a stepper motor that are both going to run off of our 12 volt rail, and therefore we need a 12 volt regulator to go with those. And so we take the values from section 1, put them into this 12 volt power rail in section 2. We have our total current, get a subtotal, and then usually you want to add a safety margin. I like 25%, but you can add more safety margin if you want. This is for a couple of reasons. So one, particularly inductive devices, like solenoids and motors and such, when they turn on, there is a power surge, and they need more power to get started up. So it's kind of the equivalent of cranking a car back in the old days of cars. You've got to insert energy into the system in order to get things moving. But also, the 25% safety margin takes into account all of the passive components and the small components that we kind of ignored before to make sure that there's enough power so we don't have to count them individually. So that will give me a final number, and in this case, it's 1 amp for this particular power rail. And then I can go and choose a regulator for that power rail based on that. And here I've found this 7812 regulator will supply 1 amp, and so that meets my requirement. Now, once I figure that out, I need to go and take the 12 volt regulator part and add it to my major components up here, because we're going to use that later on to make sure that we have enough battery power for our system. Now, I'll repeat the same process with the 5 volt power rail, and with, if I have a 3.3 volt power rail as well, I'll repeat that same process. And so again, putting in the information, how many microcontrollers do you have, how many other parts do you have that are going to run off the 5 volt power rail, calculate it out, add the margin, and then go ahead and figure out your total. And then you can choose a regulator that supplies more current. It's always okay to have more current in a system than you need. It's rarely okay to have more voltage going into a component than it specifies. So the key is current is extra current in your system is okay. So here you see I've actually got 50% more current than I need, but extra voltage is not. Since these are 5 volt microcontrollers, I need to have it on a 5 volt power rail, and that's a requirement. And then repeat the same process with the 3.3. And again, if I were designing this system right now, I would go back and look and say, okay, is there another Bluetooth transceiver that I can pick that will run on 5 volts? And then choose my regulator and put that regulator up into my major components. So once you've figured out each of your power rails and what the requirements are for those power rails, then you bring the power rails down here so you can calculate the overall power required for your system. So you take the regulators for each power rail, put them in here along with the maximum current that they're actually using. And again, we're using maximums because this is all worst case. So the goal is to make this as universal as possible so that you will not have brownouts in your system. So there are other ways to calculate the current as well that are more precise, but this is a safe way to do it while we're learning how to build systems. So I put in my 12 volt regulator, which will supply an amp and therefore draw an amp. A 5 volt regulator, which will also supply and therefore draw an amp, and the 3.3 volt regulator, which will supply and therefore draw half an amp. So that gives me a total of 2,500 milliamps of current required for my supply. And again, these are all estimates because they're different voltages and such, but it's a safe estimate. So based on that, I know that since I'm using a battery in this system, then I need at least 2,500 milliamp hours or milliamps of power that the battery can supply for a useful amount of time. Now, if I'm using a power brick, then what that means is I'm going to need a minimum 2.5 amp power brick that would plug into the wall. But in this case, we're going to use a battery, and so the idea is I'd go out and find a battery, and here I found 1,500 milliamp hour batteries, but I'm going to need two of them, and if I use two of them, then that will give me 3,000 milliamps total, which is greater than my 2,500 milliamps. Now, battery capacity is measured in milliamp hours, and so in this case, I bring my battery down here to step 4 if I have a battery, and say, okay, well, I've got two batteries at 1,500 milliamp hours per battery, so that gives me 3,000 milliamp hours, and therefore I can calculate the battery life. And here it's going to be 1 because I've got, actually, I'm sorry, no, it's not going to be 1. It is going to be it's going to be 3,000 divided by, oops, not that one, 2,500. So my total current required of the supply. And that's going to give me 1.2 hours. Now, this is where, again, a design decision comes into play that you may need to redo this battery selection because let's say that for my application I need it to run for more than 1.2 hours. Then I either need to add more batteries or choose a different battery in order to bring that number up. And that's something where you want to think about your user and what they might need. One last question that sometimes comes up is what if you have multiple printed circuit boards with different power supplies? So for instance, remote sensors where you've got like a base station and then it communicates wirelessly to some sort of remote sensor station. If that's the case, then you need a separate power budget for each of those systems because they have their own power supplies. Now, and you'll also need a separate schematic for each of those as well, because if you put them all in the same schematic, then the net lists will mix and bad things will happen, and you won't get the outcome that you're expecting. So it's better to put each of those into a separate schematic project. I hope this helps you understand the power budget. If you have any more questions, please see me or the TAs. Thank you.